This is a review of section 1-3. The topic is and or as logical operations, and the way they function with De Morgan's laws, which are something that were around for quite a while before De Morgan got to them. But in the middle of the 19th century, he's the one who actually came up with some notation in order to be able to write it down, and he included it in a book. So he gets credit for this. They call them De Morgan's law. The first thing you need to know is what and or mean. And is pretty straightforward. It's the same as what we use in English. P and Q, in order for that to be true, both P and Q have to be true. If I say it is cloudy, and then I say it is raining, if those are P and Q, and then I try to put them together and say it is cloudy and it is raining, well, that's only a true statement if it is cloudy is true and it is raining is true, just like in English. The other one is a little more complicated, but not too much. The sentence P or Q. If I say it is cloudy or it is raining, well, if we find out it's cloudy, then I'm right. If we find out it's raining, then I'm right. In fact, if we find out it's cloudy and it's raining, I'm still right. The only way I can be wrong if I say it's cloudy or it's raining is if we look outside and we see the sun is shining and it's neither cloudy nor it's raining. And so that means my statement is false. So let's see what that looks like. I mean, that's what's right here. Let's see what that looks like in terms of a truth table. Okay, here is the truth table that goes with that. The way you read a truth table is simply P can be either true or false. Q can be either true or false, and the way the two of them can combine is they could both be true, they could both be false, or one could be true and the other could be false, and these two are the ways that can happen. And for and, if P and Q are both true, then P and Q is true, and otherwise it's not. And for or, P or Q is true if both of them are true. If one of them is true, it's only false if both of them are false. This paragraph is kind of interesting, and the example they give here is, would you like coffee? Yes. Would you like cream or sugar? Yes. If I ask you, do you want cream or sugar? You could want cream and you could want sugar, and that's okay because I'm offering them both to you. That's called an inclusive or, because I'm including one or the other or both. Sometimes there's an exclusive or. You can have French fries or a salad. Yes. What do you mean, yes? Well, I mean, I'll take French fries and a salad. No. You can have French fries or a salad. You can't have both. We still use the same word for both of those. We use or to refer to both the inclusive and the exclusive. I say, would you like cream or sugar? And I'm not really giving you a choice between the two. I'm asking you separately, do you want one? Do you want the other? And it's okay to choose both. With French fries or salad, you only get to choose one of them. That makes that exclusive. When we're doing logical expressions, or always means the inclusive. So that means for or, if both of them are true, the or is still true. So here are the logical expressions, and you can combine them, P or Q and R. You always do what's inside the parentheses first, and let's see what happens after that. Oh, and logically equivalent just means that you get the same truth values for both logical expressions. So here, these two things are logically equivalent. I can say not P and Q. I can also say not P or not Q. These two mean the same thing. And the way you find that out, the way you see it, is by setting up a truth table that looks something like this. And then you start to fill it in. As you start to fill it in, you take the first one, P and Q. This is what P and Q look like. That's true if P and Q are both true, otherwise it's false. And then here's not P and not Q. All right, if P is true, then not P is false. And if Q is true, then not Q is false. So we've filled in those two columns. And now that we have P and Q, we can figure out what not P and Q is. And it's just the negation of this. So we go down here, and you can see that this negates to false, true, true, true. And over here, when you're doing not P or not Q, not P or not Q, when they're both false, then the or statement is false. Otherwise, if one or both of them are true, then the or statement is true. And you notice that you've got the same truth values here as you do here. False, true, 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 false, true, true, true. So saying not P and Q, or saying not P or not Q, those are equivalent statements. And that's called De Morgan's law. That's one of the two De Morgan's law. It's symbolically stated like this. Number one, not P and Q is equivalent to not P or not Q. There's another one here, not P or Q is equivalent to not P and not Q. They didn't do the truth table for this one. I'm just going to use the P and Q that's already here, and I'm going to say P or Q. That's if one or the other are true. So here we've got true, 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 and then false. Right? That's following this, 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 and this. And so not P or Q is the negation. So that's going to be false, 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 true. Okay. Just carrying over from P and Q here, not P is false, false, true, true. Not Q is false, true, false, true. And if I want to know whether these two combined with and are true, so this is not P and not Q, right? Just to make sure it fits in the camera here. These two are false, so this is false. These two are not both true, so this is false. These two are not both true, so this is false. These two are both true, so that's true. And again, you've got this truth value and this truth value are both the same. So that means not P or Q, right, is equivalent. That's the 3 lines here, like an equal sign, but with 3 lines instead. Not P and not Q. Your book does not use the Venn diagrams that I used in class, but when you look at the Venn diagrams, you can see, let's do the not and first. You'll notice that the first Venn diagram here shows A and B. That upside down U means and, or intersection. And the yellow area there is A and B. And then for number 2, it shows you not A and B, and that's everything that's not in the center there like that. So the yellow in the second one is not A and B. And you notice the little apostrophe there, that's yet another way of saying not. We're going to stick with the one notation that we're using, the little squiggly line, but as I go to find graphics around the internet, sometimes they'll use other notation, and that's okay, we can live with that. If you look at number 3, that shows you what not A is, and if you look at number 4, that shows you what not B is. Those are the two yellow areas there, and if you combine them, not A and not B, it's everything colored in except that center section. So if you look at number 2 and you look at number 5, those are the same. The same thing is true for the other one of De Morgan's laws, where you're looking at not A or B. The way you find that is to take A or B first and then negate it, which is what the first 2 pictures are in the left column. And then in the right column, you take not A, which is the first picture, and not B, which is the second picture, and you find where both of them share the coloring in. So if you look at the first picture and the second picture, you see that the only places where both of them are colored in is around the outside of the circles. And that makes the picture on the left at the bottom the same as the picture on the right at the bottom. And so the equivalency statement at the bottom of the whole graphic there is true, that not A union B is equivalent to not A and not B. That is pretty much Morgan's law, and that's really what this is all about. If we go back over here and look at page 22, and we're looking at the questions that are there, to express the following inequalities by writing out each implied and or. This actually says that x has to be greater than 3, and it has to be less than 4 or equal to 4. So this is x is greater than 3 and less than or equal to 4. Here, give the truth value of P and Q if P is true and Q is false. Well, in order for P and Q to be true, they both have to be true. If they're not both true, and they're not here, then P and Q is false. For what truth values of P and Q is the statement of P or Q true? Well, the truth values here, P has to be true, or Q has to be true, or both of them have to be true. So it could be P is true and Q is true. It could be P is true and Q is false. Or it could be P is false and Q is true. The only time this isn't true is if both P and Q are false. Complete the truth table below. Well, here, P and Q. Maybe we should do this with a piece of paper as well. Okay, I'll do it this way. Okay. P and Q, that's true when both of them are true, and not true if either one of them is false. So this is true, false, false, false. And now here we have P or P and Q. Well, we have P and Q here, and we have P here. And in order for an or statement to be true, only one of them has to be true. The only time it's not true is if both of them are false. Here, P is false, P and Q is false. So this is false. Here, P is false and Q is false, and that's false. Here, P is true and P and Q is false, but that's okay. Okay. And here, P is true and P and Q is true, so that's okay. So notice the truth value for P or P and Q is actually the same as just P. Right? So these are equivalent statements. Okay, why would that be? Let's think that through for a minute. Well, here, if P is true, this is obviously going to be true because P is true, and it doesn't really matter whether the other one is true or not. So that makes these two true. If P is false, then this one over here is going to be false because P and Q means they both have to be true. If P is false, this is false. And if P is false, then they're both false. So if P is true, the whole thing is true. If P is false, the whole thing is false. That actually makes sense. Don't let that worry you. Two of the columns should be the same in your answer to part A. What does this mean? We just did that. It means that P or P and Q are both equivalent logical expressions. So let's do 6 through 8 here. In mathematics, the word or is always used in the exclusive sense. That's actually false. We just did that a moment ago, and we said, no, it's the inclusive sense, which means if they're both true, that's still okay. That means or is true. The negation of an and statement is an or statement in which each component is negated. What does that even say? Okay, let's see. The negation of an and statement. So here's an and statement, P and Q. And here's the negation of it. And that says, is an or statement in which each component is negated. So here's P or Q, and we're going to negate each component. Yeah, that was De Morgan's law. We just did that, right? Not P and Q is the same as not P or not Q. And you'll notice, I mean, you don't really refer to this as the distributive property because it's not, but it's easy to think of it that way. If you distribute the not sign into the parentheses, the operation changes from and to or. And the same thing goes the other way. Is that what, yeah, that's what number 8 is going to be. The negation of an or statement, like this, P or Q, right, is an and statement in which each component is negated. So again, here's the negated component here, negated component there, and we make it an and statement. The same thing is true here. If you're going to distribute the not into the parentheses, that's going to give you not P, not Q over here, but it's going to change this operation from or to and. Okay. Use the method of example 2 to prove the second of De Morgan's laws. Example 2 was, oh, that's the one we actually did already. This was example 2. We used it to prove that, and then a few moments ago we did the truth table for the other De Morgan's law, so we don't have to do that again. Let's see, over here, let's go back over to this side. What have we got? Use one of De Morgan's laws to express the negation of I want orange juice or I want grapefruit juice with my breakfast. Okay. The negation of that would be, well, in English, we could say, I want neither orange juice nor grapefruit juice. But what De Morgan's law says is, I do not want orange juice and I do not want grapefruit juice. So the neither nor is sort of the negation of or. Right? In English, we do that. We keep the or together and negate it by saying neither nor instead of either or. But if we, most people would think in terms of, well, do you want orange juice or grapefruit juice? And the answer would be, no, I don't want orange juice and I don't want grapefruit juice, which actually is an example that makes it pretty clear that the logic we're using here is the same as the logic you use every day. We just do it a little more formally. And use one of De Morgan's laws to express the negation of the sentence of question 2. That was the one where we said x is greater than 3 and, let's do this here. X is greater than 3 and less than or equal to 4. I don't know if you learned this way or not, but this actually means 3 is greater than x. I'm sorry, 3 is less than x, and x is less than or equal to 4. And so if I were going to turn this around, I would say 3 is greater than or equal to x, because that would be the negation here, or x is greater than 4. Okay, so this would be the sentence, and I guess if I were writing it out in English, I would write it out the same way I'm going to read it, which is 3 is greater than or equal to x, or x is greater than 4. And when you're doing it on a number line, I mean, let's even just do that for a moment and show what we're talking about here. Here's the number line. Here's 3. And let's put 4 over here. Okay. So if x is greater than 3, it means we have an open circle here. And if it's less than or equal to 4, here's our area here, and this is a solid point. And if I wanted to do the negation of that, the negation of this is going to be everything that's not colored in gets colored in. So this would be a colored in dot. This is not colored in, so we would color it in this way. This is colored in, so we'd leave it alone. 4 is colored in, so we'd give it an uncolored dot, and then we would do this. So in terms of the drawing, that's how we would negate it. And it says right here, 3 is greater than or equal to x, right? 3 is greater than or equal to x. In other words, x has got to be way down here or here. Or x is greater than 4. Greater than 4 means it's not that. Or it could be any of those. So that is what this says here it is the negation of that there. And that brings us to the end of covering the reading.